I'm Steve Jackson from U.S. Geological Survey, Southwest and South Central Climate Adaptation Science Centers. And today I'm going to talk about ecological transformation and ecological novelty. I'm going to take an approach inspired by the Roman two-faced god, Janus, who was able to simultaneously look back into the past and forward into the future. So I'm going to try to provide both past, present, and future perspectives on these topics. So the school book ecology that we were all taught, what I call normal ecology here, was mature communities that were broken up in time by various cycles of disturbance and succession. So you might have a mature forest community, a climax community undergoing a disturbance that could be a fire, a wind throw, a flood, and then going through a number of successional phases that would ultimately bring the system back to something very similar to the previous mature community. And so this was a very static view where the communities would simply cycle through multiple disturbances, but that overall the mature endpoint, the climax, would be very similar to the pre-existing one, potentially with some change as the environment changed. But we're seeing now something happening on the landscape that's a little bit different from this. We're seeing much larger disturbances than we've ever seen recorded historically before. We're seeing them all over the West with these large fires, with large mortality events and so forth. And notably, what we're seeing in the aftermath of many of these events is vegetation recovery and recolonization that is taking it on a different trajectory from the pre-existing vegetation. In other words, what is coming in the aftermath of these disturbances is not leading in a direction that would take it to what was there before the disturbances. So a key question that we have is, in the face of rapid and unprecedentedly rapid climate change and these unprecedentedly large disturbances and mortality events, what does the ecological future hold? So instead of looking forward, I'd like to look the other direction, like Janus, into the past and take a quick tour of ecological history, which is where I've spent most of my research career. Ecological history is valuable as kind of a gateway drug to help us get out of the present. We're trapped in the present. If you assume that successional cycles in forested systems require anywhere from 1 to 5 or even 10 centuries to run their full course, then we don't live long enough, and we haven't been ecologists long enough to really see those processes play out in the long term. So ecological history gives us a way to escape the present and look at what kinds of things actually happen in the longer term, particularly under environmental change. And it's also valuable in opening our minds to alternative realities, in particular alternative futures, getting us thinking about something that's not like what our historical experience has been. So some historical perspectives, if we look at the really long term, the last 65, 66 million years, it's obvious that we live in a world of change. We've gone from an extreme greenhouse planet to an extreme icehouse planet with steadily decreasing global temperatures that ultimately led a couple million years ago to the icehouse of the Pleistocene. And Here we have a view of the past 500,000 years of the Pleistocene with these alternating glacial and interglacial cycles, about one cycle every 100,000 years on average. Again, alternating between extreme glacial states and interglacial states of the same kind that we've been in for the past 10,000 years. And we actually spend most of our time in purgatory, somewhere in between full glacial and full interglacial. We spend probably 80% or more of our time in that intermediate state, which is also highly variable. The past 10,000 years, as you can see in the upper diagram, have been relatively stable temperature-wise. This is the period in which the ecosystems that we're familiar with developed. This is the period in which human civilizations have developed and prospered. But of course, we are on trajectories that are taking us out of those norms of the Holocene. Even zeroing in on the past few hundred years, the past 1,200 years in this case, there's certainly still a lot of change and variability, even though temperatures have been relatively constant. There's been some temperature change and variability. There's certainly been a lot of hydroclimatic variability occurring on interannual scales, decadal scales, multi-decadal scales, and centennial and multi-centennial scales. This high frequency and mid-frequency climate variability occurs as a result of complex interactions between atmospheric circulation, ocean circulation, sea surface temperatures, the land surface itself, vegetation cover, and the global cryosphere, the ice sheets, continental and the floating ice or sea ice. And these lead to these complex patterns of hydroclimate variability through time that are non-stationary, where no 2 years within a decade are identical, no 2 decades within a century are identical, no 2 centuries within the past millennium have been identical. Again, it's non-stationary variation with very complex patterns as a result of this interaction. If we look at natural communities across North America, natural vegetation, and look at it from a paleoecological standpoint to ask ourselves, how old is that vegetation? What's the antiquity of that particular community or ecosystem? The answer is different in different places. In some cases, the communities are only a few decades old. In other cases, they're a few centuries. In other cases, a few millennia. But it's very rare to find ecosystems, terrestrial ecosystems, that date back much more than 10 to 11,000 years ago in North America. To illustrate the kinds of dynamics that we see, I'll just give you a couple of vignettes. If we go to the coastal plain of South Carolina and look at the longleaf pine forests there, here's a 30,000 year pollen record from the longleaf pine system. And for the past 6,000 years, the system hasn't changed a whole lot. It's been pine dominated, predominantly longleaf pine. There have been some changes in both the fire regime and the openness of the canopy that are probably a product both of hydroclimatic variability and also Native American burning practices. If we go beyond 6,000 years ago, we see any number of other vegetation states dominated by oaks and pines, or by oaks and various other hardwoods. Then when we go back to the last glacial period beyond 16,000 years ago, again, we reach relative stasis and pine dominance, but the pines at that time were jack pines, a boreal species, very little oak, in contrast to the pine-dominated communities of today. So there's been considerable turnover, even though this system has been relatively static for the past few thousand years. Now, here's another example from the Upper Peninsula of Michigan in the mixed conifer hardwoods forest. This is the past 8,600 years. And you can see here that there's been considerable turnover in the forest composition over that period, with dominant species declining, other species moving in, colonizing and attaining dominance, species rising and falling in sequence in response to slow changes in temperature and more rapid changes in the hydroclimate. At this site, there haven't been any periods in the last 8,600 years where the vegetation composition, the forest composition, has been stable for more than 1,500 years at a time. It's rapid turnover, relatively rapid turnover in forest composition, and continual emergence of communities that are novel with respect to that particular site. It's continually emerging novelty with the communities of the past 1,500 years having no historical precedent at any time before. The communities between 3,000 and 1,400 years ago having no precedent from the previous times. So continually emerging novelty, continual turnover. And this is characteristic of what we see over most of the globe at these longer time scales. If we go back to the glacial maximum, this is a study in which we did a comparison we took all of the sites, nearly 600 of them, from all over the world that had vegetation records dating back to the last glacial maximum 20,000 years ago. And we asked the question, how different was that glacial age vegetation from the natural vegetation of that region today, both compositionally and structurally? And you can see that in most cases, the answer is very different. Anywhere between 2/3 and 3/4 of the sites show major large-scale compositional and or structural alterations since the last glacial period. Only a fraction of the sites show little or no change. So ecological transformation, we're realizing by our experiential norms, is a new normal, but actually looking back into the past, ecological transformation is also the old normal, at least in the long run. And this is valuable perspective for looking ahead into the future. It tells us that change isn't new, that species populations have a fair amount of resilience and adaptive capacity to be able to undergo these kinds of changes and maintain themselves, or to move to new locations. So looking to the future, to the fabulous Anthropocene era that we are now well into, what does the future hold for us? Well, that fabulous future is going to be very different from the experience of the past century, the past several centuries, in fact. Ecological transformations, large-scale changes in vegetation composition and structure are likely in store at a global scale. The left-hand diagrams show the RCP 2.6 scenario, which we've probably overshot. We're probably not going to be able to get get onto that trajectory without some pretty severe measures. The more likely scenario, the pathway that we're currently on, is RCP 8.5, and that is one that bakes in large-scale vegetational transformations pretty much all over the globe. Again, the RCP 2.6 forecasts some change, but not nearly as extreme as the current business as usual trajectory that we're on. So, of course, as conservationists, we'd like to know something about what those emergent ecosystems are going to look like. Can we forecast them? Well, forecasting ecological responses to global change isn't easy, particularly when it comes to composition of communities. This is an exercise that compares a number of global terrestrial carbon models. These models are relatively simple in terms of the kind of dynamics they're trying to model. It's biophysics and plant ecophysiology. And in 2006, all of the models were run using the same climate drivers, past, present, and future. And you can see that the models diverge very, very widely in their forecasts of land carbon uptake. Some of them predict a lot of carbon uptake. A lot of them predict a lot of carbon loss. And we think, well, 2006, that was 14 years ago. The models have improved. We're learning more science. We're getting better parameterizations. The same group did the same set of experiments with the improved models 8 years later in 2014 and found pretty much the same thing, this trumpet bell, or as some of the folks in the global carbon modeling community call it, the cone of shame. And this is a relatively easy problem compared to forecasting community composition. Community composition arises from three primary factors. One is the nature of the physical environment, the climate, and the soil. It is also determined by species interactions with each other, and it's also determined by contingent dynamics, neutral factors of chance dispersal and colonization and disturbance and so forth. And all three of those factors are influenced by climate. Biotic they're complex. They involve species moving across the landscape, both native and invasive, interacting with each other in complex ways. Each species is responding to the physical environment, and its interactions with other species are being influenced and mediated by the physical environment, including climate. Looking at the physical environment itself, we're going to be seeing environmental novelty emerging over the next few decades, where new climate realizations will arise and some existing climate realizations will disappear. So with novel climates, there's no place we can go on Earth to look at the vegetation corresponding to those novel climates. The climates don't exist, so it's very difficult to anticipate what things how things might arise. We can model it, but again, it's we do have difficulty in simply doing this empirically. And then finally, with the neutral factors, we've got multi-scale climate change and variability occurring at annual, decadal, multi-decadal scales. We've got multi-scale spatial heterogeneity in the environment, and then we've got ecological processes that play out across a vast range of spatial scales and temporal scales, all the different kinds of processes ranging from individual responses to the environment, to population dynamics, to community interactions. So this creates cross-scale interactions and leads to yet another dimension of uncertainty, highly historic in contingent outcomes. I'm looking out my window at the Santa Catalina Mountains outside Tucson. Much of that range was burned in a severe fire in June and July of this year. The vegetation of that mountain range in 2050 or 2100 is going to be very different in the aftermath of the 2020 fires than it would have been had those fires not occurred. And so we're going to see that kind of contingent dynamics playing out. It's been going on for some time across the West. And again, this creates indeterminacies and uncertainties. So ecological stasis is no longer a norm. If the goal underlying conservation is to prevent change, then failure is inevitable. And that would happen whether or not we had a human-caused climate change or not. In the long run, things would change anyway. But the problem is, how do we manage under this rapid anthropogenic climate change that's underway? So we need to be developing what might be called a post-normal conservation, a conservation of ecosystems under change. This is a huge challenge, but also an opportunity for learning and for experimentation. It's going to require advancement of our understanding of the physical environment and how it changes. It's going to require great advancement in our ecological understanding and knowledge base. It's also going to require the social sciences, and not just economics and political science and decision science, but also the values dimensions. It's going to require philosophy, ethical considerations, valuation of landscapes, and so forth. This is a grand interdisciplinary challenge that we face, and that we're going to have to work very quickly and very diligently on. It's hard to know right now in 2020 what we can do today that our counterparts in 2050 or 2100 will look back and thank us for. And I think that's one of the reasons we need to take an experimental approach to this. We don't know exactly what's going to work, and what works will probably depend on what happens in 2050. So that's where Chief Christensen's ideas about shared stewardship agreements that she talked about in the earlier plenary can play a role, that by coordinating across the landscape, we can take advantage of the patchwork of ownership and jurisdiction to try to develop an experimental approach to managing and responding to climate change, to figure out what works and what doesn't, and to hedge our bets for the future. So I'll just conclude by saying post-normal conservation, it isn't rocket science. It's much more difficult than rocket science. Thank you.